Today we'll talk about ordinary least squares regression, or just regression, just about the simplest model that powers data science. Nowadays, we live in the age of data, more variables, more information. Surely that means a better model, right? Well, one of the biggest mistakes in modern analytics is assuming that if a variable is available, we should include it. And in today's abundance of data, it's tempting to throw everything into the soup and let regression sort it out. But sometimes, adding more variables doesn't improve the model. It can actually make it worse. Which is why on top of ordinary least squares regression, we have one of the most important tools in statistics and data science, and a relatively more recent one as well, called Principal Components Analysis. OLS, the workhorse. OLS has been around for about 200 years or so, way before the age of personal computers, but continues to be useful up to this day. Its job is beautifully simple. Find the relationship between a set of predictors and an outcome, while making the overall prediction error as small as possible. In two-dimensional space, it amounts to drawing a line through a cloud of points, such that the sum of squared errors from the line to each actual point is a minimum, which gives it its name of ordinary least squares. In higher dimensions, the idea is still the same, although the graph is harder to visualize. It's not a line anymore like in two-dimension, as it becomes a hyperplane in n space. But the intuition stays. Yes, it's harder to visualize, but it's not harder to compute, as solutions have become so available and easy to run using software and computers that it's everywhere. It's built into Excel, it's built into R, it's built into Python. For example, this equation means we have three independent or input variables x1 up to x3. We have four coefficients, the constant b sub 0, and the three coefficients b1 to b3, and the dependent or output variable y. Now, a small side note. Here, y is a linear combination of the x variables, which keeps this formula linear rather than being graphically linear in n space. For this reason, I actually prefer saying OLS regression for this kind of regression involving least squares rather than saying linear regression per se. This avoids the impression that the graph is always a line, when in fact, linear regression for high dimension space does not mean the graph is a line, but simply means that the output variable y is a linear combination of the input variable x's whose exponents equal 1. So this is linear, and this is nonlinear. Finally, a linear regression need not be exclusively an OLS regression, as there are other kinds of linear regressions aside from OLS. Anyway, almost every analyst, economist, scientist, and data scientist uses OLS. It's so common and easy to use that we often take it for granted. But there's one assumption we violate surprisingly often. Here's the temptation. Imagine we're predicting a person's shoe size given his height in feet. But we also have their heights in centimeters and in yards. So now we have three predictors instead of one. Sounds better, except they're all exactly the same information. Centimeters and yards are just different ways of describing the same height. We've added variables, that's true, but we haven't added knowledge or any incremental value. OLS now has to figure how much credit belongs to feet, how much belongs to centimeters, how much belongs to yards. And there isn't a meaningful answer. The variables are competing to explain exactly the same thing. And this is multicollinearity. Consider this hypothetical data. Now, let's suppose we run the OLS regression using Excel as follows. If we do OLS mindlessly just because all the variables are available. And here's the output. Notice that the model is significant, explaining almost 80% of the adjusted R-square. But the coefficients don't make any sense. The p-values say that only the intercept is significant. And there's an error message even for variable 1. This is indeed not very helpful. Now let's do PCA on this, and if you're not familiar yet with PCA, we suggest that you first watch the PCA videos we are sharing below if you still haven't. Let's now compute for the correlation matrix, and it is this. Immediately, we already see that all the x's are perfectly, positively correlated. Not surprising at all because it's the same variable but just expressed in 3 different measurements. And doing PCA, we have the following. Again, we use QuantProf to work the eigenvectors and eigenvalues. And here we see that only one principal component explains 3 out of 3 or 100% of the variation of the correlation matrix. That means there's only one component rather than 3, which we can think of as the height factor if we think of factor analysis. Or if we think of variables, we can pick any one of the 3 variables to represent the height factor. More about factor analysis in the future, but things should be apparent from the foregoing between what is a factor versus what's a variable. In this case, we really just need one variable to represent the height factor. And let's choose height in feet. The resulting ordinary least squares regression is as follows. And this is the graph. Now the graph gives you y equals 3.9x minus 11.95. The p-value suggests that the coefficients are significantly different from 0, and the r squared is almost 100%. So it's a very good model fit. Now it makes sense. And what looked initially like a linear regression with 3 independent or 3 input variables was really just a bivariate regression with 1 independent or input variable. Of course, nobody intentionally builds a model using feet, centimeters, and yards together like this. We just did it like this to drive home a point. In real-world, multicollinearity is much more subtle. Think about predicting house prices. You might include floor area, living area, number of bedrooms, number of bathrooms, total rooms, and each variable seems reasonable on its own. But many of them are measuring nearly the same underlying idea, the size of the house. We have a previous video on this using PCA and OLS. You can check again the video description below for that video. When datasets contain tens or hundreds of variables, this overlap becomes almost inevitable without you ever knowing it. And that's the danger of throwing everything into the soup. More variables don't always mean more information. Sometimes they're just mere redundancies. And this is where PCA comes in. This is exactly where PCA shines. Instead of asking OLS to untangle dozens of overlapping variables, PCA does some housekeeping first. It looks for variables that carry essentially the same information and compresses them to a much smaller set of independent components, either into a smaller set of variables or even factors, if it can glean how the remaining variables get easily grouped into. This is the meaning of dimensionality reduction, where even our simple example showed how powerful PCA is for compressing and reducing data requirements. In today's world of abundant or big data, the challenge is no longer finding enough variables. It's choosing the right ones in a sea of data. PCA doesn't replace regression. It helps regression focus on the information that actually matters by removing unnecessary overlap. And that's why these two techniques, PCA and OLS, are so often used together. If you enjoyed this video, please like and subscribe. And if you'd like to support the channel, check out my Ko-Fi page linked below. You can download the QuantProf Lite Excel add-in for free. Just enter 0 for the donation. Or if you found this helpful, just buy me a cappuccino. Every bit of support helps me create more content like this. Thanks for watching, and see you next time with even more skill building in data science. See ya!